All right, ladies and gentlemen, 10 o'clock. Welcome back to your senior design seminar. We've had quite a bit of a since the last seminar, um, but hopefully we're getting back on track here now in quarter number two. So quarter number two, we have 5 seminars on the lineup this quarter. So we're going to go every other week, usually on even weeks, but we delayed 1 week here into week 3 for Dr. Sevier's talk, just because of his availability. So today we're going to be seeing a talk by Dr. Sevier. Before we sort of get into our talk with Dr. Sevier today, I do want to peel the curtain back a little bit and give you guys a little bit of insight into senior design, why you're taking senior design, where it falls into the curriculum, and specifically like why we're going to see a talk from Dr. Sevier today about engineering without borders. And this is something I wish someone would have told me when I was an undergrad going through the undergrad engineering program. And I'm going to peel back the education curtain a little bit for 5 or so minutes before we get into the talk with Dr. Sevier to tell you guys kind of the process of engineering education and the accreditation that each school has to go through to have certified engineering degrees. So before we get into the seminar today, I just want to talk about Abet accreditation. So you guys have probably heard that or seen that if you've been looking at jobs where it says something like Abet accredited engineering degree is required for this job. You might look at that and say, okay, what is Abet accreditation? Well, I want to talk about that a little bit right now. Abet is the accreditation board for engineering and technology. And Abet lays out a series of guidelines for each school that each school has to follow in order to be certified as like an engineering education school. And so without ABET accreditation, the power of your engineering degree would be basically nothing. So MSOE every couple of years has to go through ABET accreditation to prove that its engineering education is sort of up to snuff. All right. And ABET has a website that you can go to and look at what they think is an important information for you as engineers to know going through an engineering education. I'm going to pull up that website here really quick, and one little snippet of that particular website that sort of shows what ABET thinks is important for you guys to understand and know coming out of engineering school. And that's going to lead me into what I think is the reason why we're having certain seminars this particular quarter. And so if you go to the ABET website, you can come upon this little nugget of information that talks about what they think students should be able to do when they're done with their engineering education. And so here we have criteria 3, student outcomes. So this is the website that ABET lays out and says, when an engineer's done, they should be able to do these 7 things. The first one is identify formulas, solve complex engineering problems by applying principles of engineering. Okay, you do this in basically every single class. All right, anytime you're doing like a typical homework problem in your thermal class or a typical, you know, exam question in your statics class, whatever, you're doing this. Okay, but in order to sort of satisfy the criteria of ABET, we have to do a lot of these other things. And a lot of these other outcomes that we're hoping to instill in you, a lot of them actually come from senior design. Okay. So right away, number 2, an ability to apply engineering design to produce solutions that meet specified needs with consideration of public health, safety, welfare, as well as global, cultural, societal, environmental, and economic factors. Okay, this is where Dr. Sevier's talk comes in today. So Dr. Sevier is heavily involved with Engineers Without Borders, and he has a very awesome presentation today where he's talking about how a group of engineers went down to Guatemala, assessed a certain design that they sort of needed to tackle, and in their design process, they had to consider a lot of these sorts of things: economic factors, cultural factors, environmental factors, global factors. And so this particular seminar is designed to point you towards what is the second ABET outcome, which is, can we get you thinking about design in terms of like a global or environmental or a cultural perspective? And so when you listen to Dr. Sevier today, I hope that you'll keep this like outcome in mind, is like, how is the design that the group that he's sort of presenting about, how is their design different because of the cultural or environmental or societal impact that happens to be in this particular situation. So this is Abet Accreditation. We're going to see a lot of seminars this quarter that are sort of very pointed towards these particular outcomes. All right. And as we go through the seminars this quarter, I'll maybe peel back a little bit more of the curtain. So without further ado, I hope Mike is in the talk here. Dr. Sevier.
I'm here.
Here. Okay, good. So I'll stop sharing my screen here and I'll welcome in Dr. Sevier. So I don't know, Dr. Sevier, if you want to sort of take over on the mic here, and we'll get you going. Maybe you can share your screen as well and make your way through the presentation. And so thanks for coming. Here's Dr. Sevier with a talk on Engineers Without Borders.
All right. Thanks, Kevin. It was pardon me, we're in front of students. Thanks, Dr. Hart. And then I'll go ahead and I'm going to share my screen now, and then I'm going to go ahead and go to presentation mode, so hopefully you can see the whole screen. Cool. All right.
Yeah, looks good, Mike. And I'll encourage the students, if you'd like to ask questions about the presentation during his talk, please type into the conversation chat, and I'll sort of pop in as I see fit. Okay. So go ahead, Mike.
Sure. Sounds good. Yeah. And now I should point out right here at the beginning, Dr. Hart said I was heavily involved. I want to make clear that I wasn't involved in the design process. I'm presenting about work that was purely done by students, and I don't want to take any credit that they deserve. And I know at least one of you is out there that traveled with this project. So anyway, a lot of the students did all the work. I've just been a very fortunate observer to see the work that they did. And I'm going to do my best to give my interpretation of the work they did with this Engineers Without Borders cardamom dryer retrofit. And this is actually what was done and implemented in 2019, right around Thanksgiving break. And since then, they've actually been working on further upgrades to the system. But this is the one that was done previously. So let's go ahead and see like the motivation of this. The project is really a combination of Engineers Without Borders and Heifer International. Larry Paul from Heifer International, who is the head of the Guatemalan office, presented this chart to us in the context of a much larger presentation about this problem that Guatemala is experiencing with heavy deforestation. And one of the causes, not the only cause, there's a lot of causes that are contributing to this, but one of the causes is using dryers for spices, but primarily for, even coffee, but primarily for cardamom. Cardamom is the major export of Guatemala, and it's great. It's a great crop for them, but using wood is one of the primary causes of deforestation. So that's what they came to us with, trying to figure out what to do about it. So here's another slide showing one of the dryers with an operator next to it, and you can kind of see the heat exchanger up on top. Kind of taking the air in. The air is pulled in by a fan down here and sort of thrown into the pila. You can see like that big circle object on the bottom left side. That's the pila. That's where all the spice is. Cardamom is the major spice that we're taking a look at. And so the basic drying process is they'll go ahead and blow hot air into the pila for a few hours. I might say a few hours, I suppose more like around the lines of 30 hours. And then eventually they'll get cardamom that they'll say is good quality. And really they use wood instead of propane or some other natural gas because it provides the premier color. And apparently color is the determination of quality, not more so, I guess, than how much it tastes, which is kind of interesting, but it's kind of an interesting insight as to what drives consumerism. And so for that reason, so they can get essentially the most profit possible, they tend to gear towards using wood as the fuel source, the primary fuel source. Now, once again, I should note that this whole process is the problem of wood being used for the dryers, and the fact that deforestation is happening. Not to mention, as a result of the deforestation, the cost of wood is increasing, and so the profit margin for the dryer operators and the farmers and everybody that's involved in the supply chain is affected by this, right? And so there's an advantage to the operators in that they'll have a larger profit margin by having increased efficiency of these dryers, and of course there's an environmental benefit by using less wood. And so that's the major motivation for this project. It's an interim project or an interim solution, because there's actually they're trying to redesign a whole new dryer that they hope can be implemented, but in the meantime they want to start helping the situation as soon as possible. So they found the first step in a design process, and I like to think of this is not just design but even analysis in general. Once we get outside book problems, where you have a like a legitimate problem, and there's infinite complexity, really, right? But like the reason that we don't go into the complexity with most of our problems, by dealing with like quantum physics or quantum mechanics, and instead use like Newtonian laws, is because there's not a whole lot of benefit to be gained going that deeply, right? And so essentially what we try to do when we solve problems or design is we try to look for where is the biggest gain going to be made, and usually it coincides with the least amount of effort, right? You hear this in other forms too, where the 80-20 rule. A lot of times people will point out where you'll get the 80% of the benefit with 20% of the effort. Okay, so that's essentially that's not a hard and fast rule, but it generally holds true. And so they looked at where can the biggest impact be made, and they realized that a lot of the heat is lost in the heat exchanger, and so they try to figure out how can we improve this part of the dryer first. And now they've started looking into other processes, but this is where they've looked first. And here we see their initial solution. Pardon me, I say their initial solution. This is the final design for this iteration. They're working on other processes now, but essentially what we have is a piece of sheet metal that's being held up, and that sheet metal has been cut and twisted, and the whole goal of this twisted piece of sheet metal that we've called swirlers, and they've also been called turbulizers, is merely just an attempt to take the air that's being drawn into the heat exchanger and mix it up. Mix up the cooler air on the inside, right? Just mix up those laminar layers so that the heat that's being warmed up from the outside gets transferred to the inside. Cold air from the inside goes to the outside. You increase that delta T, and so more heat can be transferred. So that was the goal of introducing these swirlers. Okay, so it's a nice, simple, elegant solution for a number of reasons. One, it turned out that there was actually a significant increase in efficiency. They're also very simple and cheap to implement, which of course is a major concern with working with a country that does not have the same means as we have to everything, and this is something that they could implement pretty easily, where they do have access to sheet metal, they do have access to metal shears, they can implement these, and so this is a nice, elegant solution. And so the next thing we want to talk about is how do you come up with this elegant solution? And the answer is a mess. And I wrote all these arrows out there, not that you need to follow the arrows, but if you can follow the fact that it's somewhat convoluted, then I think you got the major point of this slide, where I drew this brain here because I feel like most of the stuff that we do in an engineering school, and for better or worse, I feel like it kind of needs to be done this way. It's mostly a left side of the brain type situation. What's a linear method for solving these problems, right? Only solve it this way. I recently had a student in a class, he didn't like the way that I was using MATLAB Grader. Some of you that are in my classes, I guess I apologize if you don't like me using MATLAB Grader, but he didn't like it because it didn't allow for creative solutions. And I had to let the student know that when it comes from looking at stress equals force over area for a truss, there's not too many other creative solutions that you can use, right? So most of the stuff that we do is left brain, and it's okay, because like a lot of stuff we just have to like know, like, yes, calculated stress in bending, MC over I. We know what that is, right? But now that you're entering into this design portion where a lot of it is more right-brained, right? Which means that which is uncomfortable, and it's uncomfortable because we're unfamiliar with using that portion. Many of you have been involved in design your whole time here at EWB, which is awesome, and a number of the different clubs that you're doing, and Engineers Without Borders being one of those clubs. They had to get really comfortable with not knowing what the solution is, not knowing the direct process. And so they had to, try to figure out, like, well, what types of changes can we make? First of all, it's like, should we do a complete redesign, or should we just retrofit? And eventually they highlighted retrofit, and then they thought, okay, well, how should we retrofit it? And they thought of, like, very big changes that could be implemented, right? Like a completely different fuel. But they realized that that might not be easily available, or it might be too expensive. And so those ideas were disbanded. And so then they tried to start thinking about other things, and they also realized that they needed more information, and they were very good about consulting experts. Some of the experts were professors in this own department. I know Dr. Dr. Cook helped out a lot with this, and they also went to industry, and they still do have regular meetings with industry partners. 2 hours a week, they'll talk with them about, hey, we're thinking about this, what do you think? And they kind of iterate ideas back and forth, and they'll take those ideas and start working with those. So there was a lot of iterations in trying to figure out how to do this, and even when they started realizing, like, well, maybe we can just start changing the way the air flows in those pipes. Once they got to that, they even had a couple of ideas. And so here's what they had. Here's one of the ideas that they had with banged up pipes. Now it looks like a fancy design, and maybe they thought of it actually being fancy. I think this was actually a precursor to some CFD that they wanted to perform, and they considered doing that, and then they eventually, through a few iterations, came upon the swirler design that we have. And so even though and then once they came upon this idea of just a metal insert, some other questions arise, and those questions are like, well, like what's the optimized shape? Like what's the best configuration that we can use for this? Because of course, there's a lot of different ways you can bend this. There's a lot of different sizes that can be incorporated. Not to mention, like you're trying to make this available to a number of different heat exchangers that don't have a uniform pipe diameter, and so they were really trying to figure out, like, what would be the best configuration. So they had a lot of ideas, and I kind of want to show this slide to show, like, sort of like different levels of the design process, where you kind of have like a gross portion where you're just trying to figure out like a basic design to go with, and then, like, even when you find like a basic design, then you have like more minute optimizations. Well, the next question is, of course, like how to optimize. And we have different options, and this is probably what you're going through right now. Like, well, should you use test? Should you use, in this case, we have CFD, computational methods, right? A lot of times, I know what other professors and I have talked about with some of our senior design teams is, like, well, just taking like existing data that's out there and trying to find like some method of interpolation between that data, right? There's a lot of different ways you can optimize these. It turns out the bottom CFD picture that we have that was created by Tanner Vakulik, I believe. I think it was eventually disbanded. It was used primarily just to show how the laminar flow is eventually kind of swirled. But those of you taking CFD realize that to get meaningful results from CFD really requires an expertise in what you're doing, and oftentimes requires such a high level of detail that it doesn't necessarily make it the best choice. So a lot of times you just go straight to test, and that's exactly what they did here. Up at top, you can see that they have an example of an insulated pipe where they have thermocouples at different stages within the pipe. Okay, they have they kind of measure the regular temperature within the pipe from a heat source, and then they have a heat source being provided at one end of the pipe via a heated wire that's coiled around the exterior of the pipe. And they essentially used a vacuum to suck air through the pipe. And it seemed like a relatively straightforward type of test. And I know from discussions with the students that they really encountered this data that was not clear, thermocouples that were not working. They had fluctuations in what the vacuum was producing in terms of airflow. They were getting inconsistent results. They were getting all sorts of things that just didn't make sense. And I really applaud them for dealing with that in such a calm way, where they still tried to stick it through and try iterations and still consult different experts. I think Dr. Cook helped them a lot, and Dr. V helped them a lot, specifically with this test, where they did their best to try to still obtain some meaningful results. And I think it's such a great example where, with our analysis, we can get such accuracy with MATLAB up to 16 digits, and we're so proud of that. And here in test, eventually, we get humbled to the point of like, I just want to find something that's semi-meaningful, and I really applaud them for persevering and being able to do that. Okay, so that's just like before we went down to Guatemala. Now we have like what happens when we actually implement it in Guatemala. What I have here is really just a show of wood being stored in different piles, and on the left pile is essentially what one site that we were at measured to be a cubic meter. Maybe that's 2 cubic meters. I forget exactly now where the different posts were, or the measuring system. But you'll notice that one's stored outside, and it also looks wet outside because it was raining, and on the inside, of course, it's dry. Well, of course, like the burning properties change depending on the moisture content of the wood. We went down there with the typical engineering school type of mindset, where we had all these control parameters we wanted to implement in this experiment, where we were going to test without swirlers and with swirlers, and try to have like the exact same type of wood that was being provided, really closely monitor the temperature that the wood was at, the moisture content, and monitor like the temperature fluctuations within the dryer itself. And we had all these ideas of what we were going to do to get it really precise, really control the variables as much as possible. And when we went down there, we realized that just wasn't going to be possible. They were the masters of their operation. So much of what they did was based off feel, as you can imagine from an expert in any industry. A lot of times, you watch a master cook, they just like start throwing stuff in the pot at seemingly random to me, but they just have a feel for what's right, and they had a feel for what was right in their process. And we found it was very difficult to even determine like where they were picking wood from, and so anyway, it became very difficult. Now I showed like this slide to bring about the wood example. I was arguing or debating about showing another slide, which was some of the travel challenges we had with fitting 20 people or 30 people on the back of a small Toyota pickup, which I thought was pretty fun. but there were other problems. But this I wanted to highlight just some of the difficulties in the actual implementation of the experiment. Okay, and so what I wanted to finally highlight, though, is like, despite the craziness, and despite the fact that, when we did the experiment, and even things that you didn't think you could really argue about, as terms of like, well, how much wood was burned, and they had a number, and we had a number. We didn't argue with them because they're the experts. This is their baby. Like, you don't come in and tell them what to do. We just found that there was a difference there. They also measured the drying time differently, which was a surprise to me. But fortunately, they thought that there was more of a savings than we thought there was in terms of efficiency. Regardless, I wanted to highlight those difficulties in all stages of the design process, right? We talked about like just one, like how do you come up with this idea? All the different people that you interact with. Two, you come up with like, okay, we have like some ideas of where to isolate our ideas. What's the major design we should do with? Okay, we found a major design. How should we optimize that design? And then like you try to implement that design. Then you run into struggles there. Like it's just like struggle. I think for a very left-brained person, and I can throw myself in there, having like my whole life been doing analysis, right? Like it's very difficult to try to like adapt, like there's this growth period that's uncomfortable, but I think like once you get through the growth period, you actually get to this very interesting place where you're more present, and you just see these problems not as like a disaster, but it's just like, well, this is just an iteration point. This is just the information that we have now, which was cool, and it was great to see at the end. Here we show Nikki Weiss, who is now showing some of the dryer operators, like, hey, here's how you implement these swirlers. They were very excited about the savings that they experienced. So there's a few pictures we have of some of the students that were on that trip helping create these swirlers for their own use. And then on the right, we see a picture of the travel team. Oh man, I think Lucas is cut out. Sorry about that. I was trying to like use fancy things with PowerPoint. You might tell like all these slides. I just decided to just take to take some of the suggestions that they have. I don't know if that's like slide protocol or not, but anyway. So there's most of the team that was there. Sorry, Lucas, and. Talking with Larry Paul, in charge of Heifer International, who was very excited about the work that they did, and is now starting to work on how do they get this implemented in more dryers to get more data about its usefulness, its effectiveness, and two, of course, like, well, hopefully give the farmers or give the dryer operators more profit, and then also help save the deforestation, help reduce that as well. So he was really excited about that, and that process is very interesting as well. A lot of it coincides with trust. And it was awesome that Larry Paul was able, or the team was able to develop trust with him and with Heifer International, and they have like a whole method of developing trust within the communities. To start implementing this, as well as a lot of other programs that Heifer's involved with. So I'm very proud of what they did, and I feel fortunate that I got to observe a lot of the process, and that I got to go on the trip for really no other reason than, as I was telling Dr. Hart earlier, I happened to be a faculty member whose wife gave him permission to go. so that's really all I had.
Yeah.
So
very cool.
Thank you.
Very cool, Dr. Sevier. Thank you for sharing that. There's a lot of like nuances here, and a lot of I think a lot of cool bits of information in this talk. A lot of similarities, I think, to maybe what the students are going through right now when you're talking about like going through an iterative design and maybe potentially thinking about doing some testing of their own to optimize and all those sorts of things. I think those kind of ideas are probably like ringing pretty true with the students right now. But some of the other things that you discussed, I think, are things that maybe aren't as relevant to the designs they're going through right now. And those are kind of the things that I wanted to highlight. And so some of the things along the lines of like cultural differences and environmental differences and economic challenges that maybe the students had when they went down to Guatemala that the senior design students here don't necessarily have. So I've got a couple like questions here I prepared for you. Maybe you can do your best to answer these, if you will, with really the focus on kind of the differences between maybe what the students are going through now in ME 490, 491, but versus maybe what the students did in EWB. And the first one I want to talk about is just like supply chain. So like when we think about, designing something in the US, ME 490, 491, like we've got McMaster-Carr, we've got Granger Engineering. Like if I wanted like a 20 pack of quarter 20 bolts tomorrow, I could do that. If I wanted a 1/4 inch thick steel, 1 foot by 1 foot piece of aluminum 6061 in the mail tomorrow, I could have that. Right. Not necessarily the case where you guys were, right? So I just want to maybe give you an open floor here to talk about the supply chain that was available there. What materials did you have? What materials didn't you have? And are there things you wish you had access to that you didn't? And how did that sort of like drive their design generally?
Gotcha. Okay. So, I think that kind of coincides with any design project. You kind of have like your design parameters and your design variables, right? Like what are you trying to optimize in it? And a lot of times, cost might just be a parameter. Like, hey, do the best you can, but it's got to be under this budget. And or you can only use these materials. In this case, like we knew that the likelihood of these being implemented. Here I am saying we. I should really say they. I say the students. Like this is their design. I had the honor of observing what they were doing. So they knew that this was something that needed to be optimized, right? They knew like the amount that the average Guatemalan dryer operator makes in a year compared to like what would be like even like a mediocre salary here is quite different, right? So one is like access. What do they have access to? And that's something, right? McMaster probably doesn't ship easily to Guatemala.
Yeah.
But two is just like, even if they could, like, what's the cost? Well, it'd be more for the shipping process, right? And not only that, part of the thing that with Heifer and Engineers Without Borders is like they don't want to be reliant on international products, right? They want to be reliant on local product, like support the local economy. And so they were concerned with like, hey, like let's make sure that they could go down to like their local tool and hardware store and get what they need, right? And in this case, I think that the team really was able to optimize on a design that fit just that. And it wasn't like their only option, right? They also had some of the very initial concepts required like a complete redesign of I think the heat exchanger altogether. But that redesign would have incorporated materials and fuel sources that they didn't have. So I think what they isolated on here, owned in on, is a nice example of something where they did have access to sheet metal, or if they could get it relatively easily.
Sure.
They could get metal shears, and I think they did a good job optimizing that component of the design.
Yeah, I think that's a luxury that we in the States have, right? Like if I'm doing a design and I'm thinking about, okay, do I need to fasten this joint to this joint with a bolt and a nut, a fastener, or do I have to glue it? Well, we have the luxury of making that design decision ourselves, but maybe in Guatemala they don't have the fasteners that they need, and so they have to glue it, right? And so how does that affect the rest of the design? And that is just a very like extreme example, but that is something that people might not necessarily always consider, is like, what is the supply chain? How easy is it to get this bolt if it fails, or get this machined part if it fails, or whatever? And so this is something maybe I think is important to drive home for the students a little bit, is when you're thinking about your design, you have to think about supply chain, what you have access to, how easy it is to replace if something goes wrong, like all those sorts of things. And being in a kind of a third-ish world country is an extreme example, but the idea I think is baked into that, which I think is nice. Did the students have like a set budget when they went down there, or was it just kind of like do it as cheaply as you can do it?
So we had sort of a we had a major contact down there. So Steve Crow is head of the Engineers Without Borders Guatemalan office. He came and helped us out mainly because he did and somebody that he worked with, Camilo, had the relationships with a lot of the local communities. So since they trust him, he came with us, like that kind of developed that trusting relationship, and it's one of the major things that you'll see down there is you know, a completely different perspective, a completely different order of priorities. Where you know, in the U.S., you know, a lot of times we care about efficiency, and we care about productivity, and in that culture, you know, it's a lot more relationship driven.
Sure.
So that becomes a priority. So the fact that they trusted him, and he already brought he had a lot of sheet metal on his car. He just like had this huge piece of sheet metal that we brought down there. So in terms of the implementation of the swirlers, that was wasn't too bad, because we had access to, you know, almost all the sheet metal we needed to create them and implement them. So
Yeah.
and even enough to like show them how to create their own and implement those. So now that wasn't, yeah, the other budget part was food, housing, and that type of stuff. I think that was like maybe the major reason that I was brought down there, was to just essentially to pay people. But so anyway, I don't know if that addressed your question about like the cost.
No, that's good.
Budget. Yeah.
The idea that you didn't have a set budget, but you're in the back of your mind, at least the students in the back of their mind are thinking about, how do we do this more or less as cheaply as possible? And when you're going through the design matrix and thinking about what is more or less important for optimizing your particular design, if you're in an area that's impoverished, maybe the weight of how costly something is becomes much higher, right? So that is another luxury that we might have in the States here, is that we can absorb some extra cost for a more elegant or more efficient design. But somewhere else, maybe you don't have that same level of luxury to say, you know, we have $100 we can spare to make this slightly better. You know, maybe that's not possible down there, right? I also liked your hint there about the cultural differences. And another thing that's important to consider when doing a design for a different culture is what is important to them culturally might be different than what you perceive to be important to them culturally. So like you said, for us, we're all about efficiency and making it better and data driven and all this sort of stuff. But for them, it's all about culture, and this is our relationship that we have. And you need to have trust in your design engineer before you even implement it. And so I think one of the things you were discussing is that you really had to convince or sell to the operators that this thing was going to be better, right? Is that storing the wood inside is better and doing it this way is better. And I think that you needed a relationship with these people to get them to trust you, to that like what you were telling them was in fact helpful and beneficial. And that is another aspect of like your design, is like if you can't sell your design through whatever metric that is, you know, forming a good relationship or communicating efficiency or whatever, then it doesn't matter how good your design is if they're not going to go through with it. If they don't trust it, then you're going to have problems. And I think like that cultural understanding of like them having this emphasis on relationships becomes more important. So I think that's cool. Did you have any communication issues with them, like trying to explain what you're doing and what the process was? Like, how was that challenge?
Yeah. Well, so that was the other reason that it helped having both Steve Crow and Camilo there. So we typically think of Guatemala as a Spanish-speaking country, and even though that is their official language, they also have like 24 other languages spoken by the indigenous communities. And so Spanish was not their number one language. Now, the site that I was at, they did speak Spanish very well. Unfortunately, my Spanish is abysmal. I tried for, you know, the year leading up. I tried doing this program with, you know, practicing Spanish for half an hour a day. To the annoyance of my family and everybody interacting with me, I tried speaking Spanish, and I thought like, oh man, I was terrible. But maybe they brought me on board just because I wasn't afraid to make a fool of myself too.
Yeah.
But so there was a communication issue there, right? You know, not knowing the words for certain things, not even knowing how to phrase it correctly. Fortunately, Nikki, I think, did an amazing job. I got to see her working on site. Like, you know, she knows bits of Spanish. She had the opportunity to work as an intern over the summer there. And you know what what I really applaud about what she did was she wasn't afraid to keep trying. Like, you know, her Spanish was like, okay, granted, it was much better than mine, right? Like I did the best I could, but you know, it still was, she wasn't fluent, and she still did her best. But and so I think that they also resonated with the fact that, you know, she was still like trying very hard, also very humbly, you know, like, you know, that's something that comes across, like, not so much in the words that are spoken, but really, you know, a lot of our facial expressions, you know, body language, like, you know, so much, like, really, rightfully so, giving them credit for the fact that they are the experts. They like in everything that we explain, like, we think, like, we think that this might be beneficial, but always redirecting, like, they really are the experts. So trying to be as polite as possible. But fortunately, like, Steve was there to train. A lot of times, we would say something, Steve would take that and translate it into Quechua or translate it into Spanish. Pardon me, translate it into Spanish for Camilo, and then Camilo would translate that into Quechua. And so like, there was this, like, you know, a lot of barriers in the conversation.
It's like telephone, you know.
It was a little bit, yeah.
The circle with every single person. That's funny. And again, I think that comes back to, like, you're trying to form relationships, and even if you're, like, willing to make a fool of yourself to try to communicate, like, that can help build your relationship with that person when they see that you're really trying to help and really trying to communicate with them and tell them the importance of this design and what they have to do to execute it well to get it more efficient and those sorts of things. And those are things that you don't necessarily see in an engineering classroom. That's like, you know, you have to communicate and be willing to form these relationships so that they adopt and accept your design and make it happen. I think that's cool. Okay, so we're kind of getting near the end here. I just want to ask a couple final wrap-up questions. If people want to get involved in Engineers Without Borders, how might they do that? Do you guys have, like, a monthly meeting time or something?
So there's a monthly meeting, weekly meeting at noon, and there's I think that's probably a good place to start. You can reach out to me if you like. You can reach out to Tanner Vakulik. I think is one of the major people in charge this quarter. Him and Hazel Ringpiz. I gotta be honest. I don't know the pronunciation of her last name 100%, but they're doing a great job leading the. Tanner and Hazel are doing a good job leading the next stages of design. So you can reach out to them. You can reach out to Dr. Todd Davis. He's really one of the people in charge of Engineers Without Borders as a whole. And so you can reach out to any of us, and you know, we'd be happy to get you involved. And I know the mechanical design group is doing some amazing stuff. In fact, today Tanner and Hazel are giving a presentation on what they've been doing, what the mechanical side has been involved with this year. So everything that I presented to you is dated. It's old information, right? So if you want to find out what they're doing now, let us know. See if you can log in onto that Teams channel at noon, and they'll give you you'll get a perspective of the new stuff that they're working on.
Okay. Looks like we have a student comment here. Very random. That fisherman painting used to hang in my grandpa's house. Okay.
It's a very similar style, isn't it? I don't know if it was the exact same one. This is one my great aunt painted a while back, and then, you know, eventually, as it happens, you know, she passed on, got rid of a lot of the paintings, and I took it just because I figured, like, you know, if I don't know it, at least I can, if I don't look like an expert, at least I can, like, well, have the office of an expert with a fisherman painting. I like to call it a captain painting.
Yeah.
So I don't know the name of it. I just call it captain painting.
It's The Admiral by Van Gogh, apparently.
I'll use that one from now on. Thank you, David.
The Admiral. Okay. Anything else you want to add before we close, Mike? Sorry, Dr. Sevier.
No, thanks, Kevin, or Dr. Hart. You know, thanks for inviting me to do this. And once again, you know, like, if you are interested, please let one of us know to catch on to that Teams meeting at noon. to see what Tanner and Hazel and the rest of the ME group have been up to. And you know, I'd very much like to emphasize that this was the students that did this good work. I just was really just a fortunate observer to see what they were doing.
Awesome.
So.
Okay, well, that'll conclude the seminar today. We will have another seminar at the beginning of the year, January 4th. So information on that to come. I think we're going to have a local surfboard manufacturer come in and talk, and someone that actually, that actually Dr. Sevier knows quite well. So should be a good seminar next time we meet in week 4 on Monday. So thanks for coming. Until next time, we'll see you guys again.
All right, thanks again.